This call is now being recorded.
Yes, and also recorded like this. Okay. Okay, let's continue. I forgot to check. Does everybody hear my voice? If you hear my voice, please raise a hand. Yeah. Okay. Thank you. Thank you. Good. Okay. So I was talking about the PEEP doors that are inspection doors that are required for a healthy operation and a good inspection of the plant. Also up above, you see explosion doors. Explosion doors are required uh, to keep the heater safe from a structural point of view, to keep the structural integrity of the heater when you have explosion inside the heater. These explosion doors help the wave of explosion get out of the heater instead of directing it to the convection section. So they are necessary to be inside, to be planted on the heater, and they are vendor catalog items, and they have some calculations, and the explosion doors are then bought from the explosion door vendors, and I think if I remember correctly, for different duties, a minimum of one and minimum changes for different duty range as per API 560 is required to be placed on the heater. So these explosion doors help the safe operation of a heater, and my experience is that explosion doors. My problem always with explosion doors are very hard to place on smaller heaters, because you have a lot of connections on the heaters around the upper portion of the radiant section, and also the size of the explosion doors are not finalized when you are in clarification with the vendor. So it takes a lot of space, and this causes the other instrument and process nozzles to go inside together and be very close to each other. All in all, explosion doors are required as per API 560 and helps the safe operation of the heater. Okay. When you have tubes inside the radiant section and convection section, you need to support the tubes. Obviously, the tube's weight and the process fluid, the weight of the process fluid inside them cannot be supported by the tube itself. It needs the support, especially in higher temperatures, as in higher temperatures, the amount of allowable stresses for the tubes reduces. So you need to support them. In different sections, different sort of supporting are prepared for tubes. For example, in convection section, based on the geometry of the tubes, for example, in this heater, we have horizontal tubes which are perpendicular to the plane of your computer screen. You see, we have two types of we have two types of supports. The above one looks like a spoon. For supporting the tubes which are on the wall, we need a spoon type kind of support, and for the tubes which are going slightly below the roof, you need this kind of hanger support. These support are not covered with refractory, so they need to have a high alloy metallurgy to be able to resist the high temperature. Most of them are manufactured using casting process. and the metallurgy is selected based on the tables which are available in API 560. They are also high alloy metals, for example, like chrome nickel alloys, 50 chrome uh, nickel alloys, and they are manufactured normally using casting technology. And I will go through them a little bit more on next slides. So see that based on the geometry and configuration of the radiant section, you need different sort of supporting. Also, we have different types of supports here. I will talk about more about them later. Okay, now let's go to convection section. Uh, in convection section, from this side, you see that the refractory from the roof of the radiant section is continuing on the wall of the convection section. You see some shapes of trapezoids. Uh, these are these are refractory materials. You see that the arrangement of the tubes inside the convection is in a staggered mode. You see the tubes that that are staggered. So it is obvious that when we have a tube close to wall, we cannot have a tube closer than that to wall, and we have a space here as the heat transfer is maximum in a staggered position. So we would have a problem. Some of the flue gas can escape from here. So we close the path of the flue gas from here, exactly the same concept as there is in shell and tube heat exchangers. We close the gap here by adding refractory material here. And they are called corbels. They are normally done at site, and for example, with castable refractory, they are the contractor creates this shape and prevents the flue gas from escaping from the space between the staggered tubes and the wall to increase the heat transfer and force the flue gas to go back and transfer the heat with the tubes in convection section. So we have a refractory that is continued here, and in the convection section, it is shown as corbels. You see that here it is written, yes, here it has written corbel. Okay, now let's talk about the tubes here. The tubes that are here directly see the flame, and we have requirements based on API. You see that in this picture we have blue tubes here, and again blue tubes here. They are plain tubes, and these plain tubes should be used here as per API. It means that you have to have the same metallurgy for the tubes that are in convection section, but see the flame directly. How many rows of tubes? As per API 560, you need a minimum of 3 rows of shield tube. They are called shield tubes or shock tubes. Why are they called shield tubes or shock tubes? They are called as so because they shield the higher tube, the upper tubes, which are thin tubes. They shield them from flame. In older designs, for example, in 1960 or 1970, the designers used to put a refractory wall here to protect these tubes. And the criteria, the philosophy has changed by advancement of metals and materials, and there is no need to put a refractory wall here. We will use a higher metallurgy, a better metallurgy, resistant metallurgy tubes, minimum of 3 rows here, and we call them shield tubes. These shield tubes protect the thin tubes from the high radiation from the flames. And the interesting part is that you have a design theory for the tubes inside the radiant section. Also, you have the same design theory for these shield tubes, although they are in convection section, and they are they are viewed as radiant tubes in calculations, although they are placed in the convection section. Okay, we have shield tubes. As per API, we have to have minimum of three rows of shield tubes with the same metallurgy with radiant tubes. Some of my colleagues sometimes tell me that we change the metallurgy because we use lower metallurgy because they are installed higher above the flames. But as per API, this is not allowed, and you have to have the same design criteria for the shield tubes and radiant tubes. Okay, above the shield tubes, we have convection section fin tubes. I said minimum of 3 rows of shield tubes. There can be more shield tubes, and also after that, we can have either fin tubes or we can again place here bare tubes. There is no limitation for us to use fin tubes or shield tubes, but it is logical to increase the heat transfer by using fin tubes here. So we normally have fin tubes here, and keep in mind that the flue gas which is passing through the convection section, going from down to above to the stack, reduces its temperature. Reduces its temperature, and the flue gas loses energy and the temperature reduces. So the tubes experience lower temperatures when you go above. So if you have more sections of convection section, more bundles of tubes, you can use lower metallurgy tubes because they are going to experience lower temperatures. It is not shown here. It is only one bundle of fin tubes. We can have more in convection section. We normally have more than that. So you can use lower metallurgy to reduce the cost of the heater for the client. So we have fin tubes here. The fins can be different types. We will discuss them in slide 13. We'll talk more about them. These tubes are supported by something called tube sheet or convection tube supports. We will go through that. This is a tube sheet that you have probably seen in shell and tube heat exchangers. It is normally a forged or cast. It is manufactured of forged or cast material. It is manufactured of high metallurgy, high alloy metallurgy, and it has many mechanical problems. The dominant failure mechanism is creep inside these tube sheets, and they have to be carefully designed and manufactured. We buy most of them from China, and they are very big and thick tube sheets, and the tolerances and one big difference between the tube sheets here and the shell and tube tube sheets is that the tubes, because of the high temperature, the tubes are allowed to move freely inside the tube sheet, and the tubes are not welded to the tube sheets. They act as support. They act as a weight support to keep the weight of the tube and the process fluid inside, especially in high temperatures, which these movements are very, very important. Okay. So this was everything about convection section. We'll talk about more about tube sheets. Okay, we need a breaching section. We need to change this geometry, the section, from a rectangular shape to a circular shape. So we need a breaching section. This breaching section sometimes makes a lot of problems for us, make a lot of operational problem for us. Uh, that if I had time, I would go through the problems associated with breaching section. And after that, we have the stack, which helps the flue gas get out of the furnace, and we have damper to control the pressure or the draft inside the heater. We'll talk more about the pressure profile inside the heater later. Okay. Very, very hard slide it was, and it has a lot of points to talk. Okay. Thank you, Mr. Akbari. Mr. Jafari Gul, refractory means a layer inside the furnace. Or yes, we'll talk about refractory in the following slides. Yes, it is a layer of material, mostly from alumina based, to keep the heat inside the furnace. Yeah, that's right. Very thank you. API 936 describes inspection and installation, and the method to buy the monolithic refractories and is a very good help. Yes. As per API 560, if you use castable for your furnace, you have to follow API 936. This is mandatory. So we need to use API 936. Yes, I'll talk about it in the following slides. Thank you, Mr. Ekber. Okay. We talked about the configurations of the heater. We talked about different components. Now let's see real-world examples of the tube arrangement in the radiant section. The smaller one is the helical coil. So you see that it looks like a helix, and you see it needs inner structure to keep them during manufacturing and during installation, and these will be removed during installation. And you see that we cannot make the coils very big with high diameters because we cannot make the tubes very big. We have limitation on the side nominal pipe diameter of nominal pipe size of the tubes. So we can use this sort of tube arrangement for lower duty heaters. And you see here vertical coils. You see the half of the heater here. This is the vertical cylindrical coil. You see the modules that either they are installed here in the shop, or they will be installed on site. And you see here the coils that would be assembled together that are vertical. You see the coils here, and also you see these doors on these modules. They are the inspection doors, I guess. And anything else I see here? You see the bottom of the, I think it's very small, but from mechanical and structural point of view, you see that the body of the heater is stiffened using stiffeners. Also, I guess the bottom of the heater is also is being stiffened by the stiffeners. Also, they were all cylindrical type. You can also see the box type heaters. See, these are the boxes. This is the boxes, and these are the coils that will be installed inside the boxes. I guess by the looks of it, they are fabricated as modular. They will be shipped to the client's side, and they will be installed on each other before every section. First the coils are installed, then the other section comes on top. Also, you can see a smaller vertical cylindrical no, this is a stack, I guess. Uh, Probably the stack of the heaters. The platform here shows that it is a stack. It is not a radiant section. Okay. Okay. Now that we have talked about radiant tubes arrangement, let's talk a little bit about convection tubes. Uh, I went through them mostly, but not a bad idea to review that. This is the convection section. In simple heaters, uh, in simple heaters, remember that I'm talking about simple heaters. In simple heaters, configurations may change based on the radiant section, but the tube in convection section are always horizontal. Because the economizer or the convection section is installed on top of the radiant section. There is no arrangement logically possible. So the tubes are horizontal. If you make the tubes vertical, some other things might happen. So in simple heaters, we have horizontal tubes. The flue gas comes from down and exits from the above and passes from on the bare tubes and fin tubes. See that we have 3 rows of bare tubes, and the other tubes are fin tubes. We'll talk about a number of passes in later slides. Tubes are installed horizontal, can be shared between multiple fireplaces. Yes, there are some licenses that employs, for example, 2 radiant sections that come and merge into one convection sections. This is the uh, interesting thing about the convection sections. Shock tubes are bare. I talked about it in a previous slide, that why a shock tube or shield tube should be bare. And also, we have above the bare tubes, we have extended surface tubes, which these extended surfaces are known as fin, but they might be solid fins, serrated fins, or studs. Um, these fins are used in different situations. When you have a clean, non-corrosive fuel, you can have solid fins, but changing it to serrated fins reduces the mechanical strength, but gives you a better heat transfer. Up to the heat transfer area for serrated fins are something around more than 2.5 or 3 times the solid fins. So you have a better heat transfer with serrated fins, but the mechanical strength reduces. And if you have a very, very dirty fuel or corrosive fuel that needs very frequent cleaning, you need studs. Studs are welded to the tubes using electrofusion welding. ERF, yes, electrofusion welding. They have high mechanical strength, and they can be washed using soot blowers. They are the perfect choice for dirty and corrosive uh, fuels that can produce dirty and corrosive flue gases. So it depends on the process, it depends on the fuel to choose what sort of fins you use. Obviously, they should be considered in the thermal design of the convection section, the type of the fin that you use. Okay. Uh, we will talk more about the design of those sections in later slides, but for now I skip and go to other components of a fired heater package. Fired heater package, from pressure point of view, from draft point of view, can be divided in 2 major subsections. The first one is the natural draft heaters, and the second one is the mechanical draft heaters. What are the natural draft heaters? You see it as the first heater on the left. A natural draft heater is designed in a way that the flue gas itself, by the help of the temperature provided by the burner, and the stack effect can get out of the heater itself. It can transfer its heat to the surrounding tubes, and it can get out of the heater. The job of a heater designer, a thermal designer, is to make sure that a natural draft heater flue gas in different scenarios of operation is able to get out of the heater. You may ask, is it possible that a flue gas which is hot would not exit the heater? Yes, it is possible. For example, see here, you have a convection section. If you move the tubes in very close distance to each other, you block the way of the heater, the flue gas. The flue gas cannot exit the heater, and the pressure increases just below these convection tubes. You have to, as a thermal designer, you have to manage the distance between the tubes, the pressure drop, and the stack effect. You have to balance them in a way that it is possible for the flue gas to exit the heater. Okay, this is a natural draft heater. Mechanical draft heaters are divided into three sections, three types. The first one is a forced draft heater. What is a forced draft heater? It has a centrifugal fan that provides combustion air for the burner. Why do we need a forced draft burner? Forcing the air through the burner increases the amount of the amount of heat available in the same size comparing to natural draft. So by adding a fan, or by using a burner which has a forced draft fan, you can increase the amount of heat liberated by the chemical reaction in a burner. Another type, another job of the thermal designer is to make sure that a forced draft fan, a forced draft burner or forced draft heater flue gas can exit the heater safely. Another type is induced draft heater. It doesn't have any fan to provide more air for the burner, but it has a fan on the exit after the convection section to make sure that the flue gas can exit the heater safely. And the third type of the mechanical draft heaters are the heaters that both have a forced draft fan, they are called FD fan, and the balanced draft and the induced draft fans, which are called balanced draft fan, balanced draft heaters. You see that in bigger equipment, for example, in steam reforming, when you have bigger heat recovery sections, the flue gas itself is not able, due to pressure drop, is not able to get out of the heater. So you need an induced draft fan, ID fan, to make sure that the flue gas is able to get out of the heater. Another point that comes to my mind, that when you have a big heat recovery sections, for example, preheating sections, big heat recoveries like a steam reforming heaters, you cannot use natural draft heaters. It is not possible. The flue gas is not able to withstand that much pressure drop, and it cannot get out of the stack. So you need fans to help the flue gas, to assist the flue gas to get out of the stack. Yes, two types of fan blowers can be present: forced draft or induced draft. We also call the ID fan hot fan. If you take a look at API 560 or API 673, the induced draft fan in heaters is called the hot fan. It is obvious, no need to mention that these fans are centrifugal, low pressure, and can be variable drive. Of course, the price goes higher, but you have a better control on the draft of your heater. Now, I forgot to talk about a very important word, the draft. What does draft mean? As per API definitions, draft means negative pressure. So when I say I need a draft inside my heater, it means that I mean negative relative pressure in comparison to the atmospheric pressure. So draft means negative pressure. And uh, an important point is that inside a heater, you are not allowed to have a positive pressure. So I mean to say that a very well-designed heater cannot have positive pressure. Okay, let's uh, let's move on, and I think we are losing track. I'm losing track of time. I have to be a little bit faster. Okay, we have two types of dampers on a heater. First of all, we have air dampers, which help introduce the air into the burner, and we have stack dampers which help control the amount of draft inside the heater. These are two dampers, and they are available on every type of heater. These burner pictures are taken from API 535. The last part is the stack which we talked about, and take a look at these platforms. They are very important from a mechanical point of view and also from operational point of view. You need to have a platform to let the operator let the operator to take samples of the flue gas inside the stack. So there are some requirements inside API 560 and ASME STS1 for these platforms and the place that they should be placed and the height that they should be installed on the stack. Okay. Now let's go to refractory. We have three major types of refractory as per API classification. API classifies refractory in three major categories. The first one are the refractories that they have one shape. They are monolithic, which further they are categorized as hydraulically bonded castables, chemically bonded castables, chemically bonded plastics. You can read a lot about these three types in API 936. They are monolithic refractories. You can see the shapes here. They are sometimes mixed with water, or there are some methods to prepare them and to apply them. They are monolithics refractories. They have one shape, and we will see some videos of them in following slides. Also, we have brick refractories as per API 975. You have seen them in the bakery of your near your house probably. These are fire bricks, and they may have different compositions. I'm not going through the composition that are required, but they are in form of brick. They are harder to install, but they are very, very much more resistant to creep cracks inside the furnace. And also we have soft products which are mainly based on ceramic products. You see one blanket here. This is a ceramic blanket that is used in certain places. For example, soft products are used in clean flue gases on the top layer of the refractory. Sometimes they are used when high temperature tube sheets in heat exchangers are needed. So soft products are based on ceramics, and they have their own application, and they have their regulations. API 560 has talked a lot. A big part of the API is about the usage and how to install these kinds of refractories. These refractories need something to keep them and hold them in place. They are called refractory anchors. They have different shapes. This is wavy, this is V-type, and you have different types. You can see refractories. Their material is mostly stainless steel. I have worked with Inconel anchors, and they keep them in place. The anchor spacing and the depth of the anchor requirements are very well told inside the API 560. Let's see these 3 mini movies on applying refractories. This is gunning mechanism. This is a gunning method. This is like shotcrete for applying concrete on in building structures or houses. This is a castable. This is applied on the surface, the internal surface of a vessel, and you see the safety is very important here. And people have to wear masks and be important of their safety. This is one method of using monolithic castable refractories. The other one is, I think, inside the boiler. Yes, this is a boiler. The folks are applying fire brick refractories using mortars. This is another kind of refractory. It has its own limitations. Bricks. The problem with bricks is that they cannot be used in exotic shapes. So you have to have a very uniform shape to be able to use this fire brick. They cannot be cut at site. They have to be prepared and shipped and then applied. These are fire bricks. You see that they are being very careful with it, and you can check more on that in API 560 and API 975. And also the last one, we have
Block modules installation.
We have soft products. See the ceramic blankets are formed like a block. They are built and formed like a block. The anchors are being
to ensure the correct restraint.
The anchors are being welded to the surface, and the ceramic blocks
The operation is repeated by inserting modules
are
on the H-type
inserted.
anchors and installing more H-type anchors as necessary to complete the row on which you are working.
Okay. You can see more on that in YouTube if you are interested. We talked about burners. I don't want to continue, but you see API 535 has divided burners into different categories. I have taken these figures from API 533. The first one and the most famous one is raw gas burner. In raw gas burners, the fuel and the air meet at the gun point, at the combustion point. They are not mixed prior to the throat. In the second figure, premix gas burners are the burners that are partially mixed together before reaching the throat of the burner to have a good combustion. The third one is a radiant wall burner. I've worked with radiant wall burners in topsoe methanol plants in steam reformers. They have most important. They have smaller flames, and the mechanism of the heat transfer is mostly via radiation, and they increase the temperature of the refractory by radiation mechanism. You can also check other kinds of burners in API 535. Okay, let's have a break. We have a few more slides about design consideration that we will discuss in our next section. Thank you. We will be back in, please be back in 10 minutes, which would be 8:20, 8:40. Thank you.